Hello, and welcome to my talk. My name is Arash Bina. I am a principal engineer at Bread. I've been spending a lot of my time over the past few years building decentralized or distributed applications and distributed platforms, and most of that has been in Go. Recently at Bread, we used sort of a new approach, or approach that I wasn't familiar with a lot, using CRDTs to build a service. And I thought it was very interesting, and I want to tell you a little bit about it. At Bread, to give you a little bit of context, we have a multi-tenant platform, and we provide the capability to our clients to create highly configurable payment products and offer them to their end customers, to their buyers. And then during the process of the checkout, we allow them to do credit decisioning, fraud checks, and various different types of sort of workflows. And when the checkout happens, we allow the clients to sort of service those payment products using the platform. The talk is mainly divided into four sections. I'll talk a little bit about consistency, what that means in distributed systems, but I won't dive too deep into it. I just want to mention where CRDTs sort of fit in that spectrum. Then I'm going to introduce CRDTs, what they are, and how we develop them. In the third section, what different categories of them are, and how, what are the advantages and disadvantages of each of the categories. And at the end, I'll talk a little bit about, our experience overall. How was it building the system this way? So as I mentioned, I won't get too deep into consistency here, but the type of consistency we all very much used to is a sort of a strict type of consistency where we either provide that with some sort of a database. For example, different replicas of a service, they all talk to the same database. And that's how they coordinate sort of agree on a sort of a strict sequential way of events. And it's important because at that point, all the replicas can sort of agree on the exact time that events happened. And so if you ask any of the replicas what the state of the system is, they can all sort of agree, and they return the exact same response, hopefully. In contrast to that, we have a causal or eventual consistency where we allow the state of the different replicas to be mutated. And so when you make a call to a replica and mutate the state, that replica's state will be different than the state of other replicas. In that sense, we allow the system sort of to get out of sync. And then we have, instead of coordinating that in a sort of a, either with a database or in some sort of a leader, sort of a follower type of architecture, instead of that, we sort of allow these sync events to happen between the different replicas. And what that does is that it allows the replicas to sort of converge, their states to converge. In a weaker sort of a eventual consistency system, there's only a probability that convergence will happen, and it's not necessarily a guarantee. If there are two events and one of the replicas, interpret that event as the first event happened before the second event, and another replica interprets that as the second one happens before the first one, it's possible that the state of those replicas sort of diverge. And so there are different techniques that you can use, for example, to fully sync between the replicas, compare them, and then choose one of them and tell all the replicas that this is now the state of the system. And so there are different techniques that you can use. And in contrast to the sort of a weaker eventual consistency, there's the eventual a strong consistency where through a specific type of merging function, which is a lot more deterministic. So if you have two events, the result of the merge of those two events is always the same thing. And through something like that, you can sort of guarantee a stronger eventual consistency where that all the replicas will eventually get to the same state. And this is really where CRDTs fit, and that's the type of guarantee that they provide. So what are the CRDTs? CRDTs stand for conflict-free replicated data types. They're essentially, it can be anything, but for most common examples are a structure that provides methods for sort of querying and mutating, the state of a replica. And the second part of it is what we call a monotonically increasing function. It's a merge function, and what that does is that it has that deterministic sort of behavior where you have a CRDT, you have a replica with a state, and another replica sends a state to this replica. The sort of the result of those merges will always be the same thing. And a very simple example of this is, for example, a max function. Imagine if you have multiple replicas, each of them are holding a counter. If when we are syncing between them, if you always pick the maximum of the values, after a certain point in time, all the replicas will end up with that maximum value among all of them. And so that's how they converge. And that's that monotonically increasing function. The other thing that's important about CRDTs is that every CRDT would have a full perspective, a full view of the whole system. Now, their perspective, the different replicas' perspectives could be different at any point in time, but sort of the behavior of the system overall is that all those states converge to the same thing eventually over a period of time. So CRDTs are essentially a way to build a system and replicate, data without centrally, coordinate between these replicas. And so instead of that, we do periodic sort of synchronization. So there are two major categories of CRDTs, the state-based CRDTs and operation-based CRDTs. In a state-based CRDTs, which are relatively simpler than operation-based, what we have is that each replica essentially holds the full value or full state of the system of all replicas. So for example, if you have two replicas, the first replica knows about the state of the system at replica 2 and vice versa, or at least has an idea about what the state of the system is at other replicas. Now, what it thinks it is between different replicas could be different at any point in time. But the hope is that eventually they all come to the same conclusion, to the same state. The other thing that's important about the state-based CRDT is that during synchronization, the full state of all the replicas that a replica knows about is transferred or communicated with other replicas. So if I am, replica 1 and there are 3 replicas in the system, for example, I will communicate not only my state, but what I know about the other 2 replicas' state to everyone else. And then the merge function takes care of that sort of the merging between them. As opposed to that, there's the operation-based CRDTs, which are essentially, instead of communicating the full state of the system and storing the full state of the system, each replica only holds its own state. And instead of communicating the full state, it only communicates what that mutation was. So for example, if I have a counter and we increment the counter by a value, let's say by 1, if that happens in a replica, instead of sending the actual value of the counter, it sends the operation that happens. So for example, I incremented the counter by 1, and the other replicas are supposed to receive that and do the same thing, to replicate that operation. One of the important aspects of operation-based CRDTs is that message needs to be sent, be received. Essentially, the message that is sent by one of the replicas needs to be received by all replicas. They don't have to be received at the exact same time, but we want that message to be received by everyone so that everyone can do the same operation. So in order for everything to become a little bit more familiar, I was thinking of starting from a sort of a very simple CRDT concept, and then we're going to build on top of it and make it a little bit more complicated. So the simplest thing that I could think of as a CRDT is a Boolean flag. And let's say we want a flag, and the value of the flag, we want it to be true if the flag has ever been set to true. So if a flag has been set to true once, then we want that true value to be carried over and not be flipped back to false by a false event. So the way we can define the merge function for this CRDT is that, as the value, if the value of my flag is true, then I'm going to keep that value. And if it's false, then I'm going to, accept the incoming value. And if it's true, then I'm going to flip the value of the flag to true. So let's look at it from the perspective of different replicas. Let's assume that we have a system that has 3 replicas. Each of those replicas holds a flag value. In this case, the flag starts from a 0 point, it's false, and then we can see how that value is mutated over the system. Now, in this case, I want to mention that although these 3 different replicas have a flag in them and they have a value, these are effectively the same flag. It's just been replicated 3 times. These are not 3 separate flags. And so when I ask one of the replicas what the value of the flag is, my hope is that all of them can give me the same answer because they're effectively the same flag. Now, that may or may not be true at different points in time, but we will see that eventually we want all of them to become the same. So let's say a client makes a call to one of the replicas randomly here at replica 2 and sets the value of the flag to true. So in this case, if at this moment in time, if a client asks replica 2 what the value of the flag is, it returns true. But if it asks the same question from one of the other replicas, it will return false. So obviously there's an inconsistency in the system at this point. Now let's allow the system to synchronize. So, each replica picks 1 or 2 of the other replicas and sends a message, broadcasts its sort of state. It communicates its state. And in this case, replica 2 is sending a message to 1 and 3 is sending it to 2 and 1. And so you can see because replica 2 communicated its state to replica 1, now replica 1 also has the value of the flag to true, but no one really communicated to replica 3 here, and so the value of the flag stays false. If they allow another sync event to happen, maybe one of the replicas of 1 or 2, they communicate back to replica 3, and so now the whole system has the value of true. So at this point in time, if you ask any of the replicas, they all return true. Now, I want to emphasize that this happens exactly because of that monotonically increasing merge function, right? Because we are keeping the true values and we are not flipping the flag back to false if we receive a false event. And because of that, eventually the system becomes consistent. If we were to not have that rule and flip the value back to false, the system does not converge. And so it's possible that they may all end up with, let's say, the value of false, but that's not the actual, that won't be the true value of the flag, which in this case should be true. Let's look at a sort of simple code example here. And like I said, we're going to build on top of this regressively. But I have a flag here and it holds a Boolean value. And so, it's 0 value essentially when we create a flag is going to be false. Now I have a merge function. So if another flag sends its state to the receiving flag looks at its value. And if it's false, then it accepts the incoming value. And if it's true, then it sort of returns without making any changes. And so if you look at the main function, I create a sort of a 0 value of a flag. I update it to true with an incoming true sort of state, and then I will attempt to update it with an incoming false state. If we run it as we expect, this is a very simple example. It was initially false, then it became true, and then it stayed true. Okay, so let's look at it as something that's a little bit more useful. In this case, let's assume that we want to implement a counter, and the value of that counter is, we want the counter. So let's say count the total number of calls that are made to a service. Now, in this case, because the calls will be made to different replicas, so the total value, the true value of the counter would be the sum of the values of all the replicas. However, because we want those calls to be made to different replicas, and because we want to be able to ask any of the replicas for the value and be able to get an answer, then all the replicas, as I mentioned before, will hold the values of the other flags. So rather than having just one value, we will have a slice that keeps the value of other replicas. And when you're merging them, the way to do it is to use a max function, as I mentioned, which is an increasing function to sort of update our own state and always keep the sort of the max value for all the replicas. And so if someone asks for the actual value of the flag, we can add all the values together and return the answer. So in this case, let's say we have the same three replicas. Each replica has a slice, and the green sort of shows the element that a replica increments if a call is made to it and asks to increment its counter. So in this case, let's say replica 2 receives 2 calls to increment the value of the counter by 1, and replica 3 receives 3 calls. So replica 2's value is now 2, and replica 3's value is 3. So at this point in the system, obviously, if you ask different replicas for the total value of the flag, replica 1 would return 0, replica 2 would return 2, and replica 3 would return 3. But the true value that we know, because we made 5 calls, should be 5. So let's say a sync state happens, and replica 3 communicates to replica 2 first and sends its state. So now replica 2 knows about the 3 calls that were made to replica 3, and then replica 2 makes a call to replica 1 and updates the state. So now replica 1 has the correct state of 5, replica 2 has the correct state, but no one really communicated to replica 3 in this case. And so the value from the perspective of replica 3, the total number of calls is still 3. And now let's allow another sync to happen. In this case, replica 1, for example, communicates to replica 3, but it could be replica 2. And so after the second sync, all 3 replicas agree that the total value is 5. This sync, in this case, this specific example, will happen in 2 steps. But depending on how the replicas communicate, obviously, it could happen with just 1 step, or it could happen in more steps. So we don't really know, there's randomness here depending on our communication layer. And so although the system will eventually become consistent, it may, there's no guarantee that it would become consistent in 1 step or multiple steps. A simpler example of this, let's assume that we are implementing this in just 1 replica, but 3 instances, sort of with 3 elements in our counter. So if the counter has a slice, I can initialize the slice, or create a new counter and initialize the slice, and then I can increment the counter. But when I'm incrementing, I send which replica's value I want to increment, and then I increment that, and when I'm calculating the value, I add all the elements together and create that. And so if I'm in the main function, I create a counter, I increment R1 and then R2 and then R3. And in this case, because I'm using 1 slice, I would have the full value here. And so if I increment R1, R2, R3, and then at the end R1, the total counter value would be 4. And so if I run this, you see that it gives me 4. Now we can implement what we actually discussed about 3 replicas and create actually 3 separate replicas, and each of them holding a slice. And in this case, I need the counter to know which replica it belongs to. So I add an ID to the counter. And when I'm creating the counter, I would send it which replica it is for. And when I'm incrementing, because the counter knows the replica that it belongs to, it can use the ID, so I don't need to send the ID in the increment function anymore. The value function stays the same. And I implemented the sync function. So essentially now, because we have 3 separate instances, 3 separate replicas, we need to be able to sync between them. Otherwise, the values will always stay, different. So I implemented a sync function, and so a counter can send its state to a receiving counter, and the way these two get merged is through the max function. So if the receiving replica's value is lower than the incoming value, it picks the higher value. And in this case, I mutate the receiving counter, but obviously the send counter stays the same. So now if you look at the state of the system, so I increment 3 counters, I increment 1, and so from perspective of counter 1, the total value is 1, but at this point, the total value of the counter from counter 2 and 3 obviously is still 0. So I increment counter 2, now counter 2 has a 1 for its element, and then I send a sync message from counter 2 to counter 1. And in this case, counter 1 gets updated, and now it has the correct value of 2. I increment counter 3, and the 3 sends a message to 1. So counter 1 now has the correct value for the whole system. Now I increment counter 1, it becomes 4, and counter 1 then communicates with counter 2, and then counter 2 communicates with counter 3. And then I print the state of the system. The code, so we can see that, as counter 1 got updated, and then a sync happened between counter 1 and 2. Now, from different replicas perspectives, the counters values, are different. And then it goes through, incrementing the counter at replica 3, and a sync happens, and then incrementing the counter at replica 1, and the sync happens. And so eventually, at this point in time, at the step 3, replica 1 and 2 think that the total value is 4, but replica 3 thinks that it's 1. And then after another sync, all of them agree on the same counter value. So that was a G counter, which is a grow only counter. But what if we wanted to implement a counter that we could decrement its value? If we just have one slice, if we implement it the way we implement the G counter, and decrement the values, because we are always taking the maximum, the decrement events will be lost because we are always picking the highest number. So the way to implement this PN counter, which is a positive negative counter, and we can decrement it, is to have 2 separate slices. So we use one slice for the maximum increment values, and we use another slice for the maximum decrement values. Let's look at the code for a PN counter. So we have 3 replicas, same IDs, but now here I have added a negative counter in addition to the positive counter, or as negative slice in addition to the positive slice, sort of. When I create one, I initialize both slices, and when I'm doing the increment value, I am basically incrementing the positive counter, positive elements in the positive slice, and when I'm decrementing the counter, I am still incrementing but the values in the negative slice. And so when I want to calculate the total value of the counter, I add all the positive values together and subtract from that the total value of the negatives. And when I want to sort of sync, or the merge function looks at the positive elements separately, finds the maximum for those, and then it looks at the negative values or the negative counter, and it still picks the maximums. And that way it merges the 2 states together. So to make it a little bit more automated and interesting, I implemented a sort of a naive gossip function here. And the way it behaves is that each replica picks one of the other replicas as the replica that it wants to send a message to. And in this case, sends a message to the other replica and sends a state, and then the states gets merged. So there's a sort of a simple pick function that that the gossip uses to pick another replica randomly. And I implemented a utility initialize function so I can initialize everything in there. And then the main function basically seeds the randomness for the the functionality to pick a random replica, initializes all the nodes. And then really it's the part where we are incrementing the counter. So in here, replica 1, I'm incrementing the value of the replica 1. And so you can see the positive counter for replica 1 becomes incremented to 1. And then I do the same for replica 2. In this case, 2 gets incremented, and replica 3 gets incremented. And the negative values are obviously it's 0 because I haven't decremented yet. And now I decide to decrement the value for replica 1. And in this case, instead of decrementing the positive counter for the replica, I increment the negative counter, right? So in this case, you can see that from the perspective of replica 1, the value is 0, but from the perspective of other replicas, the values are 1. And actually, none of the replicas are correct at this instance because I've incremented 3 times and decremented once, so the actual value should be 2. To make the gossip function more automated, I create a ticker, and that ticker ticks every 1 second. And then at every 1 second, it does the gossip functionality, and then it prints the state. And after 5 seconds, I want the application to be done. After the initial increments and the decrement, this is the state of the replicas. And then after the gossips happen every 1 second, the values converge. And so all of them agree on the same value. Now it's possible that if you run this multiple times, because they pick random values. Now, in this case, you can see, for example, after the first gossip that these 2 values are different. So after the first gossip, for example, the counter 2 also knows the correct value, but counter 1 is not updated yet. So if you run it multiple times, you might get different results. So I modified that same implementation for a PN counter, but to make it a bit more interesting and see how the system functions in more of a live sort of system, what I did was I created 2 other tickers. So there's an increment ticker that ticks every 600 milliseconds, and what it does is that it picks one of the nodes randomly and it increments its value. And then there's a decrement ticker, which picks one of the nodes randomly again and decrements its value, but that one runs every 1 second. And then the gossip ticker ticks every 200 milliseconds. So it's possible that it may tick before an increment or after, or before a decrement or after, or multiple times between those because it's a shorter time. So you can see that the sort of the go function here is a little bit more involved, but fundamentally, when one of the tickers ticks, it prints that it incremented that value. And then when the gossip happens, the communication happens. So let's look at what happens when it runs. So you can see in this case that initially the system, starts at the 000, and then an increment event happens in this case at replica 2, and the value of the replica 2 is increased to 1. But as you can see, replica 3 also shows 1, and that's probably because after the increment happens immediately after, before the state was printed, the communication between replica 2 probably sent a message to replica 3 and updated its state. And in the next step, the replica 1 also has the correct value, and then we decrement replica 3, which becomes 0, and then increment replica 1. And so you can see that it's difficult to predict exactly, unless we print all the exact timings of the gossips and increments and decrements, it's difficult to predict what result we should expect. The important thing is that, the values don't diverge. The values keep converging to the same values, sort of, for in all the replicas. And at the end, before I kill the application, replica 2 and 3 agree, but 2 doesn't agree, probably because the application was killed before the last sync, or before the full convergence happened. Okay, so that was the last state-based CRDT I want to talk about. And so I just want to conclude the part about the state-based CRDTs and take a look overall at the advantages and disadvantages of them. On the advantage side, I think the state-based CRDTs are a lot simpler to implement, as you will see in comparison to the operation-based CRDTs. But on the disadvantage side, obviously, every replica needs to hold the values at full state of all the other replicas. So for the space complexity, you need more space than if you're only holding the value of your own replica, essentially. On the communication side as well, each replica communicates the full state to all the other replicas, and so because of that, the bandwidth for the communication is a higher bandwidth. You need more data is transferred between the replicas. Okay, let's look at an operation-based CRDT. So for operation-based, I wanted an example of, let's implement a set. And the way the set functions is that, you add an object to the set, it stays in the set until you remove it from the set. And so similar to the PN counter, we can't simply remove something from the when we add it to the set, because that function will not be increasing. So similar to the PN counter, I will have two separate sort of sets. One is an add set and one is a remove set. And when I want to add something, I add it to the add set. And when I want to remove something, I add it to the remove set. And the net value of this set is it looks at the items that are added, objects that are added, and if they don't exist in the remove set, then it concludes that those objects exist. I wanted to make it slightly more interesting. What if we wanted to be able to remove objects, re-add objects that we have already removed? So if you add an object and then remove it, that object will exist both in the add and the remove sets. And so there's no way really to re-add something that I've already removed. So in this case, what I did was I created a sort of an arbitrary rule. So when something is added, I will remove it from the remove set, but I'll also timestamp everything. And so if there is a case where two concurrent sort of events have happened, one is an add and one is a remove, I allow the addition to win over the removal. And now that's a completely arbitrary rule because I want this CRDT to function specifically this way, but you could, for example, build another one that the remove wins over the addition. And so that clock, the increasing sort of clock, that is what provides that sort of monotonically increasing merge function. So if you look at the implementation for that, I reduced the number of replicas to 2 just because this is a longer example and wanted to be a little simpler. But so we have R1 and R2 for the IDs. And now here I've implemented a clock, and the timestamp is essentially the version value for all the replicas, which is a slice of integers. And the clock holds an ID. That ID is the ID of the replica that the clock belongs to, and it has a timestamp. Now each clock can increment, sort of give the next value for the clock, next timestamp. And then I have comparison functions, less than and more than. And so when a clock is sent a timestamp, it can look at the timestamp and make a comparison and say if the timestamp is ahead or before the timestamp of the clock. And it's possible that it's neither of those. So, and if it's not before and not after, then I conclude that those events from the perspective of the clocks happen concurrently. And that's where I will allow the addition to win. The timestamp returns a sort of a timestamp for a clock. And I have a new function to create a clock. And then I have an update function where when a clock is sent a timestamp, not only it can determine if it's before and after, but it also needs to sync its own clock with that sent timestamp, because we want always to keep the maximum version of the individual clock values. So in this case, it syncs its own internal timestamp with that. So the set is actually the CRDT itself. So it has an add map and a remove map, and I have a mutex here so that I can lock it when I'm sort of mutating the values of the maps. The new set just initializes the maps, and then the value, as I described, it looks at the add set and it looks at the remove set. And if something is added and not removed, then it concludes that it exists in the set, otherwise it doesn't. So I introduced a node struct here so that it makes the functions a little bit easier. And a node essentially is a struct that includes a clock and a set. So the node can add something to its set, and to do that, I just add it to the add set and delete it from the remove set, as I mentioned earlier, and update the clock of the node. And the remove just adds it to the remove set. So initialize nodes just creates clocks and sets and adds them to the nodes. And here's the operation part of the operation-based CRDT, where I define an action, and the action is just an integer. It's either an add or a remove. And the operation struct has a node ID. That's the ID of the node that's coming from. It has an action that happened, and it has a timestamp, and the object itself, what was added or removed. I have a send function, method that's implemented on the node. And so one node can send an operation to another node. Here, all the function does is that it initializes it creates an operation, and then it sends it to the node to be processed. And so the process is really the core of the logic. So initially, I want, no matter what the results are of the merges, I want the clock to be synced to the incoming timestamp. Then I look to see if a clock, the timestamp has happened after, or the clock is before the timestamp of the event that was sent. And if that's the case, I just update the internal state based on the incoming operation. If it's happened after, it means that, or the clock's timestamp is after the incoming timestamp, then that means that I don't need to do anything. And all happens is that in the defer function, I just update the timestamp, or I sync the clock. And if the code reaches here, it means that it was neither less or more, so they must be concurrent. And so in that case, if it's an add, I add it and remove it from the remove set. And if it's a remove, I just basically add it to the remove set. So if you look at the main function here, I try to manually control the additions and the sync so you can see what is happening in the system. So initially, I add just a simple object to the first set. And so for replica 1, I have added A, and its remove set is empty. I get the timestamp, and I send it to replica 2. And so now replica 2 also has that object. Here, I remove it from replica 1, and then I sync it to replica 2, and so it gets added to replica 2 as well. Then I re-add it back to replica 1, and what that does is that it removes it from the remove set. And then at the same time, before I allow the syncs to happen, I remove it from also replica 2. So it was already removed from replica 2, but what that does is that it creates two events. One is at replica 1, that's an addition, and then one is at the replica 2, that's a removal, and they happen at the same time because the clocks haven't been synced yet. So then I sync both of them, and because of that specific rule that I want the additions to win over the removals, both of them should end up with the same object. And if you run it, that's exactly what we expect. So the add happens, the sync happens, the remove happens, the sync happens, and then the add happens and the remove happens, but it hasn't synced yet. And then I let it sync, and now both of the replicas end up with the same value. Okay, the last CRDT that I wanted to mention here briefly, and I don't have an implementation for this, but we actually use this for some of the things that we implemented in our service, is a contextual CRDT, in a sense that with this you can really implement any arbitrary object, and all you have to do is define an increasing, that monotonically increasing function. And the way we define it internally was that we look at the state of these objects, and we define an increasing sequence for those. So imagine you have a ticket, and you have a ticketing system, and you have a ticket, and the ticket can be only opened and modified and closed. Now, if you have two simultaneous or concurrent states, one is a modify and one is a close, you can say that close should always win over the modify, right? And then that's how deterministically you can merge those together. Now that gets a bit more complicated if, for example, you allow multiple modifications to happen at the same time. And so in those cases, you have to determine which modification should be applied last, or which modifications should be applied. If they're modified, the tickets have been modified. One of them, for example, represents a name change, and one of them represents a description change. Then you have to sort of have fine-tune those and decide how we want the modifications to win. One simple way to do it, for example, is that you can always allow the last sort of modification to win, but in that case, you may not see some of the earlier events. So it really depends on how you want to design the system. So on the operation-based CRDT sort of conclusion, obviously the advantage is that you have a smaller storage footprint because each of the replicas only hold their own data, and on the communication side, they only communicate the operations, which are probably very small compared to the whole state of the replica. And also you can see that you can probably build more sort of general purpose use cases with operation-based CRDTs. On the disadvantage side, the system is more complex. There are more moving parts. And so you have to write more code. And as we know, when we write more code, we also introduce more bugs in the system. So they are trickier to sort of implement and test and make sure that they are correct. And if there is a bug in the system, it will be more difficult to sort of find and address. And the last thing is that they require more reliable infrastructure because we want each operation to be received by all the replicas. We need to have a sort of a reliable infrastructure that can do that delivery. The way we implemented the CRDTs in the service, we started with concrete implementations. So because initially we didn't know what we want the behavior or what is the common behavior for all the CRDTs. So we implement them in a concrete way. But as we implemented a few, we noticed that there are common sort of a pattern, common behaviors between all of those. And so we created this interface where each CRDT can give its ID, can give its type, has a merge function that can merge itself with an incoming CRDT. Some of them need a timestamp, and so we can set the timestamp this way. And also a CRDT can prepare itself for broadcast. And that means that when I want to communicate my state or the operation or whatever it might be, the CRDT knows how to package itself into a message that gets put on the sort of the transport layer, the communication layer, and sent out. And this really helps to simplify the other layers of the system, the communication layer, or perhaps the storage layer, depending on how you implement it. So there are a few sort of miscellaneous smaller things that I want to mention here. On the storage side, obviously each replica keeps its own storage. They don't use a common storage. And so you can implement that different ways. We ended up implementing a simple sort of a memory-based, which each replica holds the whole sort of state in memory, and also file-based. And depending on your needs, depending on how critical a system is, you can use different types of storage. The other thing is that for tests to be quicker and not have specific dependencies, for example, you can use memory-based and you can use file-based for other use cases. On the deployment side, this can be deployed really as any service as long as the replicas can communicate to each other. In our case, we deployed these as sidecars because we use a Kubernetes deployment. And so the services that require access to these CRDT values, they have a sidecar that is essentially our service that provides the CRDT functionality. Another very fascinating thing that was the topic of the clocks when we were doing research on this, there's a very interesting implementation. I've referenced it on the last slide, where there's a specific implementation where the clocks have three components: a physical clock, a logical clock, and sort of a vector clock. And what that does is that it attempts to keep the clocks close to the physical clocks. As you know, in the distributed system, it's impossible to keep all the physical clocks exactly in sync. And so typically they might be a bit out of sync by a few milliseconds perhaps. There are some certain implementations that, for example, use a specific hardware to keep everything in sync. But in this case, it's an algorithm that they have used, and that's how we that was also our implementation for the clock, and that's what we used. You need a gossip layer, and essentially the communication layer can function different ways. But we use the gossip layer in which each node doesn't broadcast the whole state to all the nodes. It just picks some of the nodes randomly, and you can obviously fine-tune that on how many nodes or how often it wants to communicate. But then through this gossip, all the nodes receive the state. One of the interesting implementations that we learned from was HashiCorp's sort of the member list, and it does a lot of things happen in that library. For example, you have queues that between the gossips, messages can be queued in there, and then it communicates the whole queue, and it takes care of, for example, the maximum length of the messages and a lot of things like that. And some of the messages piggyback off of each other so that the whole system is more efficient. The last thing I wanted to mention is that I mentioned that in the state-based CRDTs, the whole state is always communicated to other ones. But there are some interesting articles as well where they implement the merge functions in a way that you can also communicate delta updates. On the testing side, so the main thing that you want to test on the CRDTs, I guess on the unit testing side, is really the merge function and the value functions, because that's where most of the logic lies. On the value functions are typically a lot simpler than the merge functions, but most of the functionality is in the merge function. So you really, and it's something that's relatively easy to unit test. So you really want to make sure that the merge functions are correct, as it's central to everything. On the integration testing side, as you can imagine, there are a lot of moving parts. The integration testing is a little bit more difficult, but we wrote several sort of utility functions that helped us to build the integration test a little bit easier and faster. So one of those is, for example, there are functions that can create multiple replicas and establish communication between them. We have functions that allow you to set the values for the replicas directly. If you want to test something that, for example, before or after a sync, the value of a replica is something sort of that what it is. You need to be able to manually adjust the clocks to be able to sort of be deterministic about the result of a test function. You want to be able to perhaps create timestamps that happen just before or just after another timestamp. Sometimes you want to be able to manually control sort of the communication between the nodes. For example, you want one node to specifically communicate to another node, and so you want to be able to manually control those in some of the tests. And then there are utility tests where you can assert essentially the consistency between all the nodes. So as the communication happens and the states change, at the end you want to be able to sort of assert that the state of all the replicas are the same. And then you want cleanup functions that can clean up the replicas and such. So in conclusion, one of my colleagues asked me if it was worth to implement this service this way, and I think that's a fair question. It's a lot more complicated than sort of the regular ways we're used to writing services. And although it's a fair question, it's also an impossible question to ask out of context, because you want to choose the right tool for the right job. And so if you have certain performance, for example, requirements, if the eventual consistency is an option for you, and all those conditions are right, then yes, it might be the right tool and it might be worth implementing. If it's not, if the function of the service is a lot simpler, if it can be easily implemented, using the sort of irregular ways that we implement services, then perhaps no, it might not be worth implementing that way. But overall, CRDTs can provide great performance because you can ask any of the replicas and it can very quickly respond back. And also that coordination on the write and mutation side sort of does not have to exist, and it happens asynchronously. On the disadvantage side, there are many moving parts to CRDTs, and they can be complex to implement. And so The testing is more difficult, and those are some of the things that we have to consider when we want to build a system this way. And these are some of the references. There were many more, but these were the ones that I think we looked at most often, and so I wanted to have them here. And thank you. That was my talk. I hope this sort of give you a different perspective, or perhaps if you knew about it, it added a little bit more to what it takes to implement CRDTs, and I hope it was useful to you.